Hi, welcome to our pre-calculus. Today's topic is domain and ranges of trigonometric functions. As you see, I have written three familiar expressions here, and it's best that we start talking about them before we get to the issue of domain and range. Well, students get confused over the issue of what is 0 over 1, what's 1 over 1, and what's 1 over 0. First two are straightforward. 0 over 1. If you have no money and leave inheritance to one person, well, of course that person is not going to get anything. So 0 over 1 is just 0. Similarly, 1 over 1, that's just 1. If I have $1 and leave it to one person, that person just gets $1. The issue is, what is 1 over 0? So in elementary school, they probably refer to this thing as does not exist. Or they abbreviate it perhaps in some fashion. Well, or maybe they call it the illegal operation. As you come to pre-calculus and go to calculus, you need to have a better understanding of where does this come from and what are the phenomena that are attached to it and close to it. It is of course true, 1 over 0 is not a real number. There is no number that when you multiply by 0 you get 1. So all of these expressions you are familiar with, they are all correct, not a real number. So the ordinary number we deal with are called real numbers, and 1 over 0 is not such a thing. Well, to gain a better understanding of this, let's go to a situation where a ratio is a common everyday occurrence. One of such a thing is the concept of pressure. Well, what is pressure? Well, what example of pressure do you know? For example, that when you deal with your tire, they tell you in a cold day, check it out because you have lost the pressure. Well, how do you measure that pressure? You say, for example, 35 psi, is that right? That is a typical number you come across. What does that mean, psi? Well, that's of course pounds per square inches. Is that right? So what is pounds? Pounds is the unit of force. And what is the square inches? That's of course the unit of area. So pressure is a ratio of force over area. So for example, if you get a glass of water, put it on your hand, it's going to exert some kind of pressure on your hand, and of course you have no problem tolerating that pressure. But if you have a knife over your hand and you exert some pressure, of course you are going to be dealing with a dangerous situation. Of course they tell you don't do that. But what is it about the knife that causes a cut rather easily? So a knife cuts because of what? Well, you say because it is sharp, but the question is a mathematical version of that concept. What does sharp mean? Sharp means because of what? Because area of blade is small, meaning when this area approaches 0, pressure builds up. It goes through regular values, goes higher and higher. If you have a substantial force divided by a small area, you get a high pressure. High pressure can easily cut through skin or even metal and such. So mathematically we symbolize this thing by saying 1 over 0 is infinity. infinity, we write it, of course, in this fashion. So again, if you have a substantial force divided by a tiny area here representing the edge of the blade, has, if it's a sharp blade, is very small, the division causes a high pressure, and high pressure, let's call it infinity. So, and that is going to make this nomenclature is rather odd. It's not, I mean, if your hand is bleeding, you don't stand there and say, well, this thing doesn't exist, let me not look at it, or that's going to be silly. So what is happening is more or less like we are telling kids in elementary school, don't divide by 0 because you don't know how to handle what's coming out. Same way that we say, well, don't play with matches, don't play with knife, don't go near a ledge, and so on. But of course, one day you have to strike a match because you eventually have to cook. So in the same way, when you come to calculus, you have to take a number and divide by 0 and understand what is going to happen. And one of the places that you come across this is in the issue of domains of functions, and then of course domains of trigonometric function. Let me just go back to the beginning of the semester. Let's go to a problem that is simpler than trig functions. So if I have 1 over say x minus 3, I have a function that's created by 1 divided by difference of your input from 3. You say the domain of this thing is what? Domain, meaning what number are there that I'm comfortable with, and what number is it that's going to create a problem for me. The domain of this thing is any number other than 3. Because if I use 3 here, I have the division by 0, and 1 divided by 0 is going to be that infinity. So sometimes we say the domain is x is less than other than 3. Sometimes say, okay, from minus infinity to 3 is fine. Jump over 3 itself and go to the other side from 3 to infinity, it is also fine. Another way that we describe it is that we draw the real number line and say 0, 1, 2, and 3, and 4. We say clip off 3, so we draw an empty circle there to say that that is excluded. So you can be to the left of this, that is this set of numbers, or you can be to the right of it, that's those set of numbers. Those are the numbers that are okay. Then when the issue comes up a bit higher level, well, what is it that happens at 3? Why are you so particular about 3? So what you need to do is to put a magnifying glass around 3 and say, well, let me look at this thing, see what happens. So I have again say 1, 2, 3, and say 4, 5, 6. So for example, if I have x equal to 4 here, 1 over 4 minus 3 is 1. If I had 5, well, it's going to be half. If I have 6, it's going to be a third. So I'm going down, that's fine. But if I have 3.5, 3.5, if I put it there, I'm going to get 1 over a half, which is a 2. If I, so at 3.5, I get 2. How about at 3.1? At 3.1, 3.1 minus 3, that is 1 over 0.1, and I hope everybody comfortable with that, that it is 10. So at 3.1, I'm going to go all the way up here, for example, at 10. I understand that if I now get closer to 3, like 3.01, then I'm going to shoot up all the way to 100. Is that right? So if I have 1 over 3.01 minus 3, so if the input of my function is 3.01, I'm coming very close to 3, and plug it there, what am I going to get? Well, you take it and divide it, you see you get 100. So the closer I come to 3, the higher up I'm going to go, and that trend is indicated by saying we are going to infinity. So we are going, infinity is going to appear as all the way up there, the high values of y, and that is So this is the graph of y over x minus 3 so long as x is larger than 3. Well, if x was less than 3, like let's draw that in green, at 2, 1 over 2 minus 3, that's going to be minus 1. At 1, that's going to be half. At 3, at 0, it's going to be a third, and so on. If I come close to 3 again, like if I come to, say, 2.5, I'm going to come to 2. If I come to 2.1, let's see if I have room here to go down that much. At 2.1, I'm going to come to minus 10. So what's happening is that my function is behaving like this. So now I'm going to minus infinity, and for that reason that we can be plus infinity or minus infinity, even though you don't see anything negative here, but that 0 is right bordering between positive and negative, so your ratio could be, in principle, it could be positive, it could be negative. You have to make room for that. And when we have a situation like this, we say we have a vertical asymptote. So we have a line that comes very close to the graph of the function. It doesn't cut the function, so I'll try to stay away from it. So x equal to 3 is a vertical asymptote of the function that is not part of the graph of the function, but your function practically is very close to that vertical line. So when we want to deal with general functions, we have to be aware of their vertical asymptotes and such. And of course, later on, we are going to see that there's also the issue of horizontal asymptote. Like if you continue going here, you see that your function is leveling off to 0, and that's going to be called the horizontal asymptote. But we are going to come back to that later on when we have uses for it. Okay. So so far, 1 over 0, something to be careful about. We want to go one level higher than just saying it doesn't exist. Sometimes that's enough. More often than not, we want to know, well, what's happening around that peculiar event. And what's happening, we have domain splitting at that point. We have vertical asymptotes. We have functions going to plus or minus infinity. These are the details we want to be aware of. Well, now you might be asking, what does this have to do with trigonometry? I haven't seen anything so far. Well, because we avoided a bunch of functions that have this kind of a flavor built into them. We have been concentrating on sine and cosine, and they are innocent functions. They don't exhibit any of this kind of problems, and so we don't see the issue of division by 0. We don't see any asymptotes and so on. But how about the other functions? Well, all the other 4 functions do show this behavior, and that's what makes them a bit more complicated, and that's why they are like pushed out of the way. Sine and cosine, somehow they are primary functions. Everybody else kind of one level lower down, but you are going to come across tangent at least that has asymptotes, and the other ones as well. Secant, cosecant, cotangent, they all have this feature. So let's just quickly go ahead and review what we had. So I'm going to use a picture of a triangle to refresh your memory about this. You could, of course, do with the unit circle. So remember, we had an angle theta, and then we had the sides of the triangle and the hypotenuse, and the primary function sine of theta was b over c, and cosine of theta was well, a over c. That's all fine. And then we had tangent of theta. Tangent of theta was opposite over adjacent. If you write this thing as b over c over a over c, Well, B over C is your sine of theta, and A over C your cosine of theta. So this is one of our important identities that we are going to be using very often. So this is sine of theta over cosine of theta. How about the rest of them? You remember cosecant of theta was a ratio of hypotenuse to the opposite. Well, what is that? That's of course 1 over sine of theta. And secant of theta was a ratio of a hypotenuse over adjacent. That's just a reciprocal of this. So that is 1 over cosine of theta. And cosecant of theta, so let me write it here. Cosecant of theta was the ratio of I already have cosine. Sorry. Cotangent of theta. Cotangent of theta is the ratio of A over B. And A over B, you can write it as A over C over B over C. And that one you can write it as cosine of theta over sine of theta. So here is what I was trying to write, which is cotangent of theta. Here's an identity, cosine of theta over sine of theta. So here's another identity. We need to be comfortable with these identities. Sometimes they are referred to as reciprocal identities or ratio identities, various names for them. So reciprocal means 1 over something. It's reciprocal. You take the fraction, flip it upside down, that's reciprocal. And these are called ratio identities. So reciprocal identity. These are sometimes referred to as ratio identities. Or similar names. Okay. Well, what is that going to do? Let's go one item at a time. Red flag is what? Red flag is that I have a ratio. Yeah, I have 4 ratios. And ratios always have the potential of presenting us with this issue. Here's a ratio, and that's what the red flag comes alongside with it. You have to go inspect that red flag, see is really anything dangerous going on, any division by zeros going on, and in fact then we have to locate that. If so, then figure out where this kind of behavior going to happen, get the graph, and so on. That is what is behind all of this. So let's go after first of these things. So the cosecant of theta, that's 1 over sine of theta. So I have a denominator. If that denominator becomes 0, I'm dividing by 0, and all of the issues we talked about is going to show up. So to investigate, does such a thing happen or not, I go intentionally set the denominator equal to 0. So why do I do that? Because I'm investigating, well, when do I divide by 0? Well, when does sine become 0? Sine becomes 0 when theta itself is 0. You remember these were the x-intercepts, pi, 2 pi, 3 pi, and the negatives of these things just negative pi, same problem, negative 2 pi, same problem, negative 3 pi, same problem. Let's see, how do we remind ourselves that there is an issue? So I come here and say, okay, do you remember what sine of theta looked like? So we had our horizontal axis labeled with these important points, and just for clarity, we are dealing with just radians, so that something specific to work on. So we are our angle is in radians. So what does sine look like? So at pi over 2 it becomes its maximum, and then it becomes 0, it becomes negative, then 0, then repeat 0, and so on. So same way here, we go to, and so on it goes. Picture keeps repeating. So now we're going to get used to graphing reciprocal of a function by just looking at it. Of course, we can always go graph by point plotting and meticulous graphing, but first time around we better get the hang of this thing by just looking and have an intuition, and not to be so glued to our calculators and such. So what happens? I'm taking the reciprocal of this. That means I'm taking one, like if this is the angle, let's see, if this is the angle theta, this is sine of theta. That's what the graph means. So I need to take the reciprocal of this, 1 over sine theta. So I eyeball this thing. Suppose, okay, this high point is 1. Suppose this is half. 1 over a half will be 2. Is that right? So I look at the length of this, say, well, this is a half. So if this was a half, just for example, well, reciprocal that would be 2. Well, what is the reciprocal of 1? Reciprocal of 1 is just 1. So at the low point, I come here, but as the function becomes small, its reciprocal becomes large. Is that right? As I go down here, like 0.1, 0.01, and so on, this reciprocal also gradually becomes larger and larger. Is that right? Just like the practice we had here, as we were coming close to 3, our value of the function was going to infinity. We are doing same thing here. As theta becomes small, I'm not going to go through numbers because it's going to distract us. As theta becomes small towards 0, sine of theta is becoming smaller and smaller. The reciprocal of it becomes bigger and bigger. So this is going to start to escape straight up, like a spaceship going straight up. Same issue is going to happen on the this side, like at this angle, like 5 by 6. Sine is a half, its reciprocal will be 2. As sine comes close to 0, when I get close to pi, my value is going to go higher and higher. So this is going to go way up. Then what? Well, now from pi to 2 pi, everything is going to be negative. Everything is going to be negative. So I have like a minus a half here. Reciprocal of a minus half is minus 2. Reciprocal of minus 1 is minus 1. Reciprocal of this minus a half is minus 2. And as this negative quantity comes close to 0, my reciprocal becomes bigger and bigger in magnitude and goes down. On both sides it does the same thing. So it's going to have a picture that looks like this. So what is happening between these two? What's happening between these two is that vertical asymptote. So wherever sine becomes 0, we have a vertical asymptote. So we have these peculiar tiles for graph of cosecant. So quickly, how do we get the graph here? It's just one of these tiles. It comes here, touches on this one, goes back up. How about this one? We draw the asymptote at 4 pi. The graph of it starts from down here, comes to this point, it touches that, and then goes back down. So it touches at 1 or minus 1, then it goes back. Okay, how do we summarize all of this? Summarize it by saying domain of cosecant. Well, we have to skip all of these points. By the way, same story happens on the negative side. There's no difference between negative and positive. Same same problem is on both sides. So if I have a asymptote on all of these places, and the picture is like a tile work that goes all the way to infinity. So domain of cosecant then becomes x other than all these trouble points. What are those trouble points? All multiples of pi. Domain is any x other than all multiples of pi. So n is shorthand for n is the shorthand for 0, plus or minus 1, plus or minus 2. All of these guys, we call them integers. Okay, integers are just that. A domain is anything other than that. You can go ahead and write intervals of if you want, but that's going to be kind of tedious to do like that. So we just write it this way. Then we say, how about the range? Range is set of output numbers you get, all the values that you get. Well, your values start at 1, and then anything above 1 is going to show up. It also can start at -1. So here is the range. That is, we can think about it this way, like if Godzilla came and compressed this picture on the y-axis, okay, it's crushed. Say this was Bambi, and Godzilla came from both sides and crushed it on the y-axis. What's going to be left of Bambi? Down here is going to be splattered here, and up here is going to be splattered all here. This is what's going to be left if you take this picture and compress it on the y-axis. So that's what is left is called the range. So the range goes from -infinity, comes all the way to -1. This is -1, and then another piece is start from 1 and goes to all the way infinity. That's what we call the range of this thing. Vertical asymptotes at exactly what you excluded. Okay, so now we write n pi, x is equal to n pi. That's the equation of these guys. So this is like x equal to pi. This is x equal to 2 pi. This line is x is equal to 3 pi. This line is x equal to 0 pi. Now that looks silly. This is called x equal to 0. X is equal to -1 pi. Well, of course you write that as minus pi. This is x equal to -2 pi. Well, then you have to repeat this thing for all these 4 functions. What is the clue? The clue is that everything depends on what is in the denominator. While we are here on the cosecant, let's just mention some other properties. What is the period of it? Period of cosecant. How long does it take for this thing to repeat itself? Like what is one period? This is one period. Then it repeats itself. This is a repetition. This is another repetition, and so on. So the period of it is just 2 pi. Just like sine and cosine, and no different. Okay, now we did this thing for cosecant. We have to go do it for, we need more room. The questions here, you can easily look it up on some table and answer it. And what we are trying to do is understand what those answers are. Otherwise, you go there and click and pick something according to some table you have made and such. So let me see. Sorry. Give me a second to see if I can. You need a lot of space here, so. Sorry for that. I should have predicted that we needed a lot of space. What now? Okay, we did cosecant. Let's do the other one. So how about secant? Secant is what? Secant is reciprocal of cosine. So whenever cosine is 0, we are running into exact same issue. So I'm investigating when am I going to be dividing 0. To do that investigation, I have to set the denominator equal to 0 intentionally to investigate that. Well, at what angle does this thing happen? Well, we know at 90 degrees or pi over 2 that happens, and at 3 pi over 2 it happens, and then 5 over pi over 2 it happens, and so on. And not only that, negative values of these things are just as bad, meaning they cause division by 0. Well, looking at that, you might think that you are being overwhelmed by stuff, but actually if you are comfortable with the graph of cosine, then everything is going to run smoothly and no problem. So again, we go ahead and 0 pi 2 pi 3 pi and so on, and say minus pi. Our problem points are halfway point of these things. So where are those? This is of course pi over 2. This is 3 pi over 2. This is 5 pi over 2. So if you want to think about it, it's like 2 pi over 2, this is 4 pi over 2, this is 6 pi over 2, and so on. And if you go on this side, is minus pi over 2, and minus 3 pi over 2, etc. The story continues, minus 2 pi. Well, what do we need? We need to have the graph of cosine. You remember cosine at 0 is 1, then comes to x-intercept of itself, comes to minus 1, comes to x-intercept, goes to 2 pi. That is the cycle of it. Is that right? Then it repeats. So that's like a 4 pi and so on. And same story on the left side. Well, can you quickly tell me where the asymptotes are going to be? Asymptotes tie in with our intercepts. Okay, so I immediately know, based on the conversation we had, I immediately know I have an asymptote here, I have an asymptote here, another asymptote here, another asymptote next intercept, another asymptote at this intercept, another asymptote at this intercept. Then what? Then let's do this thing visually. What is the reciprocal? This is the function. What's the reciprocal of it? Immediately say, okay, I'm gonna start. I'm gonna start at high up, infinity, come all the way to this one, and then go back up. And same way down here. I'm going to start from minus infinity. Why minus infinity? I have minus 0 if you wish. Minus 0. What you're wondering, what is minus 0? I only know about the zeros. Oh, well, in calculus you are going to get used to plus 0 and minus 0, or sometimes written like this, 0 plus 0 minus. So if you are hovering on this side, function is hovering around 0, but negative 0, meaning from you're approaching it from below. So that is significance of it is that it sends you to minus infinity. So the graph is going to minus infinity. If you are hovering in this why is this not right? If you're hovering here, you're plus 0, and reciprocal of plus 0 is plus infinity. So you go up here. So not only you have to get used to infinity, you have to get used to that you have two kinds of zeros, plus 0 and minus 0, and so on. So here's a tile, a piece of a tile, here's another piece of a tile, and so on. Okay, quickly, what is the domain of secant? Well, you have to avoid all of these points. Domain of secant, avoid all these points. Well, what's the formula for all of them? X, now we are going to have a little bit of a problem because it's a odd multiples of pi over 2. I cannot say multiple of pi over 2 because this is also multiplied pi over 2. It's just 2 pi over 2. This is 4 pi over 2 and so on. So I can't say just multiply pi over 2. I have to say odd multiple of pi over 2. We can make a formula for that. You can write it like 2n plus 1 to write an odd number. We sometimes code it at 2n plus 1 because like when n is 0 I am here. When n is 1 I have 3 pi over 2. When n is 2 I'm at 5 over 2. So n, again, n is integer. If n is integer, then this is same as that. So vertical asymptote is just well, let's see, domain is x other than odd times pi over 2. Vertical asymptote x is odd times pi over 2. Then what? The range, same story as before. The range, if you take this thing and squish it, somebody's going to accuse us of being violent, but if you squish this thing, it is going to become -1 to 0, and what color did we use here? And the upper side of it is going to be that. So the range is again from -infinity to -1, and together with 1 through infinity. So excuse me. What else did we talk about? So period is same as before. Period is 2 pi. Anything else you want to say? There are these, later on you're going to call them local minimum. Why do you call it local? Well, this guy is lower than that, so if you want to look for a low point is all the way -infinity, but this is called the local minimum because compared to its neighbors it is saying lowest. This one is called the local maximum because compared to its neighbor it's standing higher up. Of course these points are standing higher up than this point, but if you're just comparing to Joneses around you, well, this is standing higher. Same one. So next up we are going to, how about y is equal to tangent of x? Well, tangent of x, we said we are going to make use of the following identity. Tangent is the ratio of sine over cosine. Ratio of sine over cosine. So where does tangent get its trouble spots from? Tangent is going to get its trouble spots from trouble spots of cosine. That is, wherever cosine is 0, tangent is going to have issues with being undefined. It's going to go to infinity. It's going to have vertical asymptotes and all of that story. So cosine of x equal to 0. We set the cosine of x equal to 0 to figure out where that happens. Well, that's what we just did a second ago. Cosine equal to 0. So x is going to be odd pi over 2 or 2n plus 1 at pi over 2. Now, well, how are we gonna get a quick graph of this? Well, it all depends what you're comfortable with. For tangent is a ratio of two functions. It's going to be a bit more complicated than the two that we just did. We know, okay, so we have 0 and say pi and 2 pi. This must be now 3 pi, say minus pi minus 2 pi. We know cosine is going to have zeros here. So it's going to have its vertical asymptotes as these locations, just like the previous problem. So shares all this with the secant. Now I'm going to convince you that the graph of cosine, the graph of tangent looks like this. We haven't worked with tangent that much, so it's going to be, we're going to be a little bit rusty here. Graph of tangent is going to go close to infinity here, comes straight down to 0, cross this point, and then cross over to the other side and sink down. Kind of a featureless function. There is no turning point. It's kind of slides and slithers up there. Same thing is going to happen in each of these blocks. Exact same thing is going to happen. One of the interesting things is that the period of tangent is going to be a pi instead of 2 pi. This tile that you're going to use here, you just need from say minus pi over 2 to pi over 2, however you want to define your tile. It's going to be half the size of the previous tiles. Now, why does this go straight up? Like there is no bend in it, there is no, there's no strange event happening, it just goes straight up. One way to see that is to use the unit circle. Okay, one of the advantages of unit circle is that it gives you this idea very quickly. So in the unit circle, you remember we draw a circle of radius 1, and then here we draw some line. We are going to call it tangent line. We'll see shortly why we call it tangent line. If you have an angle, theta, well, what's the tangent of it? Tangent is the ratio of opposite by adjacent. Well, adjacent is just 1. So this is equal to tangent of theta. Okay, so if theta starts a small value and then increases, we see that the tangent just goes straight up. There is no turning around or something, so tangent goes straight up. That's what's happening here. That is, as the angle increases, tangent just goes straight up. And when we approach 90 degrees or pi over 2, well, that tangent becomes infinity. And moreover, if you are at a negative angle, this tangent is going to be this quantity, and that's going to be negative, and that's why for negative angles we go all the way down like this. And the picture repeats itself every pi. So if I am past pi over 2 or past 90 degrees, whatever value I had at the negative angles is going to repeat itself, and that makes the period of tangent to be half of what we expected it to be. So so this is the graph of tangent. So let's go see what is the domain of this thing. Domain is all x's other than odd multiples of pi over 2, or x is anything other than 2n plus 1 times pi over 2. Vertical asymptotes are exactly at those x's. Whatever was excluded from the domain, those lines. So what are we talking about? This line is x over pi. X is pi over 2. This is x equal to 3 pi over 2. This is x over 5 pi over 2. So the edges of the tile we are using, those are our vertical asymptotes. X is equal to minus 3 pi over 2. So x is odd multiple of pi over 2. That becomes a vertical asymptote. Well, how about the range? What's the range of this thing? There's nothing missing here. Like if you take this thing and squish it on the y-axis, the entire y-axis is covered, and that becomes from minus infinity to infinity. Everything is covered. What is significant, and we are going to come back to this thing later on. Right now I'm just skipping this to keep this short. The period is pi, and that is so let's put an exclamation mark. It's how is it that we came from 2 pi down to pi for a period? We are going to come and explain that. The period is pi, and perhaps that's all we want to say here. So the range we said, and then so one more round of this thing. How about y is equal to cotangent of x? Well, that is cosine of x over sine of x. All the trouble spots are going to be extracted from sine. So if you say sine of x equal to 0, at those points you are going to have your vertical asymptotes. Where did we see that? We just saw that a second ago. A minute ago we described the sine here. When sine is 0, exactly the same set of points are going to be trouble spots for us. So we have to watch out for them. X is equal to n pi. So let's see if we can be quick with this one. So we have again pi, 2 pi, and 3 pi, and then minus pi, and we are going to have our vertical asymptotes here. Where are going to be the x-intercepts? Maybe something we wanted to mention here. I'm going back. X-intercepts at x equal to n pi. Did we mention the same thing for all of them? X-intercepts at no place. This has no x-intercept. This has no x-intercept. Tangent has an intercept. Cotangent has an intercept. Intercept of this one. Intercept. So x-intercepts where the numerator is equal to 0. Cosine of x is equal to 0. X is equal to odd multiple of pi over 2. So these are my intercepts. Okay, how can we get a quick feel for what the cotangent of an angle is going to be? Suppose we are on a deserted island. We have no calculator, and the primary concern of us is what's the cotangent of some 75 degrees or something. Of course, that's exactly what you'll be thinking about if you're on a deserted island. And so here again we appeal to the unit circle. So one reason unit circle is so important is that it gives us a lot of clues about things. on a unit circle you draw this line. You draw this line. Draw this line, and you call it cotangent line. So this one was tangent line, this is the cotangent line. In what sense? In the sense that if I have an angle theta, if I draw an angle theta and I want to eyeball this thing, so what's the cotangent of it? Here's the eyeballing. You just look at that. This is the cotangent of theta. Meaning what? So again, you have drawn this thing on that beach on that deserted island. You draw a circle, you draw a big circle, and say, okay, I'm going to call this one 1. Whatever angle I care about, I draw it. Okay. Now I'm going to measure this versus this yardstick. This is 1. So what is that? Well, you eyeball it, says looks like 2 or 2.1 or whatever it is. You measure that. That is cotangent of your theta. Well, you say, why is that cotangent of theta? Well, when you apply a bit of trigonometry or geometry on that island, of course, your friend is just geometry. Says this is theta, this is theta. Cotangent of theta is the ratio of adjacent over the opposite. Okay, this is adjacent, this is the opposite. Well, what's the great thing about the unit circle is that this is 1. So ratio of adjacent to the opposite is just adjacent over 1, which is just adjacent, and that's what we said. So you just eyeball this thing. This is your cotangent. Okay. This is cotangent. So what do I get out of that? What I get out, here's the advantage of eyeballing. So you say, okay, here suppose I have a small angle. How do I remember this small angle gives me a huge cotangent? Well, here your eyeball is a small angle. When this angle is small, my cotangent is huge. Well, that's exactly what the asymptote means. It means when my angle is small, I'm hovering here, my cotangent is huge. And then after pi over 2, my cosine is negative, sine is still positive, so ratio becomes negative. So that's why I keep going down. Now can you show me visually why cotangent of an angle that is close to pi, just before pi, like 179 degrees, why is that supposed to be a negative huge number? Well, come in here, so take advantage of the fact that this thing lets you eyeball things quickly. So suppose you have an angle of 179 degrees. What does that mean? It means your angle is going like this. So these things are running into each other. So if you are at 179 degrees, your intersection is here, and this is what your cotangent is supposed to be. Well, that's on the left side, so it's negative and escaping away. So that's why it has to go to minus infinity. That's why you have, you got an asymptote down here, and the picture repeats itself. So again, one of the things about cotangent is that its period is just pi. So this was our, so your cycle here, it finishes the cycle. The next cycle starts in it's a pi, and then a pi, and so on. So what we have here, domain x other than n pi, vertical asymptote at x equal to n pi, range, again everything is in the range, x-intercept at odd multiple of pi over 2, what else, and period, of course, we are going to come back to this. Period is just pi. It repeats itself every pi. Okay. So you want to rewrite this thing in a piece of paper. Do not rely on anything digital. I'm sorry to say, you're not going to learn it by copy pasting or by having a page to go look up or anything of that sort. None of that is going to teach you. You have to write by hand on a piece of paper. You have to go analog all the way for this thing to sink in. Otherwise, yeah, it's just not going to happen. Okay, so then these questions, you open the drop down menu and you choose accordingly, according to what we said. So I'm not going to bother with that anymore. Hopefully this issue stays with you. Once you come to calculus, not only you have to do this thing for sine and cosine, you have to do this for a whole range of functions, even functions that are just temporary functions, just an exercise function without a name. You need to figure out intercepts, asymptotes, domain, range, and maximum, minimum, and a whole lot of other things. So the analysis becomes deeper and deeper as we go. Okay, hopefully you stayed with this lecture. It wasn't a mini lecture, but you do need to go through it perhaps several times to make sure everything sinks in. Until next time, good luck and God bless.